Hello everyone, my name is Taming. Today I'm going to present our paper, The Taming of the Stack, Isolating Stack Data from Memory Errors, which focuses on utilizing a comprehensive and accurate static safety validation to remove unnecessary runtime checks on stack objects that can be proven safe statically. This is a joint work with several folks from Penn State, EPFL, and UC Riverside. As we all know, there are still a considerable amount of stack-based vulnerability related to memory errors being discovered each year. Recent examples such as the two CVEs below shows that the out-of-bounds access issue caused by the use of unsafe functions. The CVE on the right in a PCI driver enables attacker to arbitrarily write to kernel space from user space by a false bound check at line 11 and 13. Thus, we can see that the stack-based memory error still serves as a huge threat of the computer security and still a hot topic of security-related research. Generally speaking, all memory errors can be categorized into three classes: spatial error, such as out-of-bounds read and write; type error, such as type confusion; and temporal error, such as use before initialization and use after free. As we can see, there are many CVEs assigned recently of all three classes of memory errors, demonstrated that the stack-based memory error is severe. In the context of the stack, spatial and type error are the majority of memory errors, while we still observe that the stack objects can suffer from temporal errors, such as use before initialization. There are lots of existing stack runtime defenses that are trying to protect the safety of the stack, and some of them also protect heap, but they all have their shortcomings. For example, some of them only targeting the mitigation of one classes of memory error, such as soft bound, fat pointers, and type sign. Some of them have conservative checks, such as safe stack. Some of them have high runtime overhead, such as baggy bounds. So the problem is that we currently don't have a comprehensive protection scheme that covers all classes of memory errors with reasonable overhead at the same time. Though we can theoretically deploy a combo of them at runtime, but the overhead is not affordable. Thus, the reality currently is the existing protection schemes still provide the really limited protections for memory safety in C. In our DataGuard framework, we focus on using static safety validation method to identify the stack objects that can be proven safe, and we aim at validating all classes of memory errors comprehensively. Based on the static safety validation results, we can protect the safe stack objects cheaply using isolation without runtime checks. Here we go to our design section of the DataGuard. The design of the DataGuard is inspired by two previous approaches. The idea of employing static safety validation to remove runtime checks is inspired by the secured framework. The secured system classifies the safe pointers to be the pointers that never involves in pointer arithmetic or typecast operations, which already gives around 90% of the pointers are safe. However, secured does not account for temporal errors, and its classification is too conservative. For example, the access of an array within bounds needs pointer arithmetic, but is actually safe. The over-approximated number of unsafe pointers leads to redundant runtime checks, and thus could lead to high runtime defense overhead. The idea of utilizing multi-stack layout for isolating safe stack objects from being tampered through the corruption of unsafe objects is inspired by the safe stack approach described in the code pointer integrity paper. In the safe stack approach, the safe stack object is moved to the isolated safe stack while leaving the unsafe objects on the unsafe regular stack. In this way, we will be able to protect the isolated safe stack objects without runtime checks. Only apply runtime checks on the unsafe stack objects on the regular stack. However, the original safe stack classification is incomplete. It does not account for type errors and use before initialization, and the classification is conservative as it classifies all the arrays and the address taking variables are unsafe. Similar to the secured, a lot of unsafe stack objects being misclassified can be proven safe and thus save the runtime overhead. Given that, our goal of the DataGuard analysis is that we want to statically validate the safety of the stack objects against all type of memory errors. We don't want to have any potential unsafe objects still remain on the safe stack. Then we want to remove runtime checks on the safe stack objects by isolating their accesses from unsafe objects. Thus, our ultimate goal is we want to protect the maximized number of stack objects from memory errors comprehensively without runtime checks. And ultimately, we want to achieve better performance. Here is our design of the DataGuard approach in 4 steps. We will go through the details of each step in the next few slides, but I would like to illustrate the big picture here. The percentage numbers on this figure is based on all of the benchmarks that we tested, including the 5 server programs and the SPEC CPU2006 benchmarks. The first step is we identify error classes for the stack objects, which means we identify the unsafe operations that may potentially lead to the memory error. In this step, we found that 72% of the stack objects have no unsafe operations and can be classified as safe. Given all the unsafe operations, the fact is that the majority of them are actually safe. For example, iterating the buffer within bounds. In order to validate that, we need to collect the safety constraints as our second step. For example, the size of the buffer at declaration. Objects are classified as unsafe if the constraint is not concretized. We find 4% of the unsafe objects. Then we proceed into the third step, the static safety validation, to leverage the collected safety constraints and the static analysis to validate the safety of the stack objects. In this step, we find 16% of the stack objects can be validated as safe additionally. However, this is not the end. Due to the overapproximation of the static analysis, many unsafe objects found by the static analysis is only used safely. So we then propose the def use guided concolic execution to verify the safety of the unsafe objects. DataGuard is able to identify additional 3% of the stack objects to be safe, and the total number of the safe objects rise to 91.45%. Now we look into the details of each step. In step 1, the claim is that many objects may be proven safe by detecting the absence of simple unsafe operation. But how do we detect them? Remember, we have 3 classes of memory errors, so we have 3 kinds of unsafe operations. Secured already counts for the spatial and type unsafe operations, so we employ their approach accordingly. Also, we implemented the use before initialization check and an escape analysis to check the temporal unsafe operations. After step 1, we denote that the pointers that are not using any such operations are safe, and the objects only aliased by the safe pointers are safe. Then after we computed the unsafe operations and collected all the safety constraints, the claim is many objects with unsafe pointer operations can still be proven safe. Then how do we design and utilize a validation approach to validate the safety by leveraging these safety constraints? Our static safety validation steps leverage static analysis for that. For the spatial safety, we leverage a value range analysis to compute the access range of the array or structure, then comparing that access range to the extracted concrete size constraint of the declaration. For the type safety, we also use the value range analysis to check the integer type casting never change the integer value. For the temporal safety, we compute the live range interval of the pointer and the objects being pointed by the pointer based on the liveness analysis. If there is any pointer use occurs outside of the live range of the object, we deem it is an unsafe temporal case. Except for these analysis, we also utilize the PDG and the SVF analysis for the aliasing purposes. To ensure the soundness of our analysis, we approximated the possible program executions and achieves relative soundness, assuming all the relied analyses are sound. Then for the unsafe objects found by the static analysis, there may be false positive cases given the over-approximated static analysis. Thus, we leverage an concolic execution to verify for each unsafe stack object identified by the static analysis whether the unsafe operations can be executed in any execution path along a stack use chain. So if it is, we deem it is unsafe. If it is not, we reclassify it back to safe. Given the well-known path explosion problem of the symbolic execution, for obtaining the soundness of the analysis, though we apply several optimization techniques such as the state merging and context sensitivity, we do not prune any execution paths from the symbolic execution. And we classify all the cases when the symbolic execution halts as unsafe. So until this step, we get all our classification of the safe object and unsafe objects. Let's step into the evaluation section. For the evaluation, the first thing we would like to show is that DataGuard improves security comparing to the previous work. We compared mainly to secured and safe stack. The default column means the results by their original design. The minimum column means the results after filtering out all the unsafe cases since their analysis are incomplete. The total column means the total number of the stack objects. As we can see, among all the benchmarks that we tested, 91.45% of the stack objects are shown to be safe by DataGuard with respect to all classes of memory errors. By comparing the results of secured safe stack and the DataGuard, we found that 50% and 70% of the unsafe object by secured and safe stack can be verified as safe statically. Thus, we will save a lot of overhead by runtime enforcement. Besides, after comparing the default column with the corresponding minimum column, we also found that 3% and 6.3% of safe stack objects by secured and safe stack are found unsafe by DataGuard. That is due to their incomplete checking. Only looking into statistics is not enough. Does DataGuard really improve security? We define the successful attack mitigation as exploit objects are classified as unsafe, target objects are classified as safe, such that they can be separately isolated and protected. We tested on CGC Binaries and successfully prevents the exploit of all of them. Also, given the attack on the control data remains a huge problem for stack safety as attacker can alter the control flow path, but will not be identified by the CFI. In DataGuard, we classified 92% of the control data on the stack are safe and thus can be protected without runtime check. Similar to the 15 CVEs of recent years that we evaluated, we successfully prevent the exploit of all of them, and the details can be found in the paper appendices. Finally, we evaluated the runtime performance overhead. We utilized the SafeStack's runtime isolation enforcement. We found that the runtime overhead is actually dominated by the number of functions that does not contain any unsafe objects, so that we don't need 2 stack frames for such safe functions, and there will be no overhead of switching between 2 frames and handling the accesses. For DataGuard, we found 76% of the functions that only have safe stack objects, while secure and safe stack found 41% and 31% respectively. And thus our performance overhead is much lower than these two, 4.3% for DataGuard, 8.6% for secured, and 11.3% for safe stack. Note that though our evaluation utilized the safe stack runtime isolation enforcement, but the same pattern of the results should be applicable to any runtime defenses since the DataGuard essentially dramatically reduced the number of stack objects that needs runtime checks. Finally, our conclusion is that we show the idea of using safety validation to provide a foundation of low-cost runtime protection for the object that accessed safely is feasible. We believe the same hypothesis also holds for other runtime protection works. The DataGuard approach provides comprehensive and accurate analysis that can both increase the scope of stack data protection and reduce overhead. Through the safety validation, we maximize the number of safe objects in terms of all 3 classes of memory errors. We achieved more security with lower runtime performance overhead. DataGuard is open sourced on GitHub using this link, and this link is also available in the paper. That is the end of the presentation. Thanks for listening.